This presentation will go through the measures of influence and why it's important to make sure that the fundamental assumptions are met before we move forward with the model. But first, let's go over what the fundamental assumptions of multiple regression are. The validity of the statistical, global, and individual tests rely on our several assumptions. So if the assumptions are not true, the results can be misleading. Even though strict adherence to the assumptions is not always going to be possible, our estimates using a multiple regression equation will be closer than it would be otherwise. So the whole reason why we want our models to meet these assumptions is so that we can avoid producing biased estimates when we use our model. These graphs can help us to visualize the relationships and provide some initial information about the direction, whether it's positive or negative, the linearity, and the strength of a relationship. Recall, the relationship between the dependent variable and the set of independent variables needs to be linear. The plot on the left shows the residual plot for the home heating cost example. The points are scattered and there is no obvious pattern, and there are both positive and negative values. Therefore, there is no reason to doubt the linearity assumption. The points in the plot on the right are non-random. There is not a random pattern, which shows that the relationship is probably non-linear. When we believe that the data is in a linear relationship, but we have with our scatter plot, we can sometimes see that they're not. Sometimes we end up transforming our data. So if we took this data and squared the independent variable, we could actually end up with a line that represents the linear relationship between the dependent variable and the independent variable. And that allows for us to see outliers. We've talked with a lot of people over the years, and it's kind of a mixed bag of how often they end up needing to transform their variables. Some people prefer doing it. Some people are more comfortable transforming their variables than other. It really comes down to the function of the type of the data that you're working with, the type of measurements that you have, how you're getting your data, and what you're doing with your data. The requirement for constant variation around the regression line is called homoscedasticity. An example that might violate this assumption would be we suspect that as age increases, so does income. But there will be likely more variation in our incomes of our 50-year-olds than for our 35-year-olds. So this condition is checked by developing a scatter diagram with the residuals on the vertical axis and the fitted values on the horizontal axis. If there is not a pattern to the plots, that means that they appear random, the residuals will meet our homoscedasticity requirement. And we did this on the previous slide based on the scatter diagram. So it is going to be reasonable to conclude that this assumption has been violated. Although it is difficult to show that the residuals follow a normal distribution with only 20 observations, it does appear the normality assumption is reasonable from both the histogram and the normal probability plot. The normal probability plot is often included in most statistical software packages. Multicollinearity exists when independent variables are correlated, which makes it difficult to make inferences about the individual regression coefficients. Another problem is they lead to erroneous results in the hypothesis tests when we're looking at individual independent variables. A VIF or VIF is that's greater than 10 is going to be considered unsatisfactory, and that a larger VIF value actually indicates that the independent variable should be removed from your analysis. And so what VIF stands for is your variance influence factor. So what that means is by including that variable into your model, you are inflating the amount of variance that's explained. And you could be inflating it in a positive way, which would make your R squared go up, or you could be inflating it in a negative way by making your R squared go down. So consider an example which relates to the heating cost as our independent variable, being outside temperature, amount of insulation, and the age of your furnace. So if you develop a correlation matrix for all of your independent variables, you'll see it above. And so you'll look to see if there's a problem with multicollinearity. Then what you can do is you'll find and interpret the VIF values for each of your independent variables. So a correlation matrix is going to show the correlation between all pairs of your variables. And the highlighted area indicates the correlation among the independent variables. Because of the correlations being between negative 0.7 and positive 0.7, we're not going to suspect any problems with multicollinearity. But then when we calculate the VIFs for temperature and insulation and age of furnace, we also see that those values are very low as well. So then you run your regression model with each of your independent variables independently, and then you put them together to assess how your overall model is able to do that. Okay, so here, model 1 just has our diameter at breast height. We have a second model that's just using bark thickness as a predictor. And then our final model has both bark thickness and diameter as our predictor variables. So then you can compare those different models. To determine multicollinearity, we will use our VIF value, which is once again just a measurement that tells us whether or not we have issues with multicollinearity. So as we see down here, we see a VIF value of 1.68. If this value is greater than 4, we would have to investigate it. But since it's less than 10, we still like to look at it to understand it. If you have multicollinearity, some ways to fix that is you can collect more data, use more variables, use fewer variables, or you can remove some of your variables from your model. Autocorrelation frequently occurs when the data are collected over a period of time. So a scatter plot such as this would indicate a possible autocorrelation issue. The test for autocorrelation is going to be your Durbin-Watson test. Residuals that are calculated by subtracting your predicted value or your y-hat value minus your observed value. And so the difference between those is what we're looking at there. So the difference between what you predicted and what you actually saw. The goal of any regression model is going to be to minimize that distance between your predicted and your observed, right? So you're going to want that predictive value to be right on. So there's actually a measurement where we look at the distance between the actual observation and then the line, and then the distance between the predicted and the actual. So that goal is to minimize the distance between the predicted and the actual. And if you do that, in theory, your predicted values will be directly on top of your actual values. So when you're looking at your residuals, you should also look to see if they're consistently high or consistently low when you compare them to your fitted values, and that they are normally distributed. So here is a residual plot, and with this residual plot, we see that the residuals are normally distributed. And this is going to be important because if my data is normally distributed, my residuals should be normally distributed, which is going to indicate a good model. When my residuals end up coming out looking like this, it's where we have an obvious pattern, then I see that we have a problem. It could be that we have a variable in there that's not statistically significant to the model. And so I could go back and look at the R-squared and find out if it's really small. If it's small, that means the model is not very explanatory. But the residual plot that looks like this is just going to tell me I have a problem, but it doesn't tell me what problem exactly I have. When I have a non-random pattern, I'm going to be looking for missing variables, missing higher order terms of a variable, missing interactions between terms, time dependency, meaning that they have to occur in some particular order.